Hello, everyone, and welcome to the Environmental Science and Engineering podcast channel. If you're new to the channel, please do subscribe so you don't miss out on our future deep dives.
Yes, definitely.
Today, we're tackling a critical area in environmental science and engineering.
It is.
That is membrane filtration for water and wastewater treatment. You, our listener, provided an amazing collection of materials.
Right.
And our goal is to extract the most important insights, giving you a clear and thorough understanding of this technology and its significance.
Yes, you're looking to, gain knowledge quickly, but also comprehensively.
Right.
We've sifted through all the details to bring you the essential information. Membrane filtration is really a cornerstone of modern water treatment, so understanding its intricacies is incredibly valuable.
Absolutely. So let's start right at the foundation.
Okay.
In the simplest terms, what is membrane filtration all about?
At its heart, membrane filtration is a physical separation process.
Yeah.
Think of it like using a very sophisticated filter to remove specific substances from liquid based on their size.
Right.
This membrane, this physical barrier, allows water and some dissolved components to pass through
Yeah.
while retaining larger particles, microorganisms, and even some dissolved substances depending on the membrane type.
Right. It's a physical barrier doing the work. Now, our sources categorize membranes into four main groups
Yes,
based on what actually drives this separation. Can you walk us through those different driving forces?
certainly. So the driving force is the energy that compels the liquid to move through the membrane. The first and most common category involves pressure-driven membranes.
Okay.
This includes the familiar terms microfiltration, or MF, ultrafiltration, UF, nanofiltration, NF, and reverse osmosis, or RO.
Right.
Here, we apply pressure, pushing the water from a high-pressure side to a low-pressure side. What's truly fascinating is how the size of the pores within the membrane dictates what gets left behind.
Okay.
Microfiltration has the largest pores, typically in the range of zero point 0.1 to 1.0 micrometer. It operates at relatively low pressures, around 0.1 to 2 bar. It's excellent for removing suspended solids and bacteria to larger stuff.
So MF is like the initial coarse filter.
Yes,
What happens as we move to UF, NF, and RO?
Exactly. As we move to ultrafiltration, the pore sizes shrink to about 0.01 to zero point 0.1 micrometer, and we need slightly higher pressures in the 2 to 6 bar range.
Mm-hmm.
UF can filter out larger organic molecules like proteins and even some viruses. Then comes nanofiltration with even tinier pores from 0.001 to 0.01 micrometer, requiring pressures between 4 and 30 bar.
Oh, wow.
NF is particularly adept at removing low molecular weight organics and divalent ions,
Right.
those responsible for water hardness like calcium and magnesium.
And then we arrive at reverse osmosis,
Yes.
the gold standard for really pure water.
Yes, reverse osmosis boasts the smallest pore sizes at the sub-nanometer level
Wow.
and demands the highest operating pressures, typically 30 to 80 bar, and even higher for desalinating seawater.
Oh.
RO can essentially remove almost everything, including all ions like sodium and chloride,
Wow.
and even very small molecules. This near-total removal,
Right.
while crucial for desalination and ultra-pure water, also means RO systems often require remineralization of the treated water to make it palatable and prevent corrosion in distribution systems.
Right.
It's a trade-off between purity and water chemistry. So as the pore size gets smaller and the pressure goes up,
Right.
the level of purification becomes much more comprehensive.
Makes sense. That's a really clear picture of the pressure-driven membranes.
Yes,
Now, our sources also detailed membranes that rely on other forces, not just pressure.
but that's right. The second group utilizes an electric field.
Okay.
Electrodialysis and electrodeionization fall into this category.
Right.
Here, instead of physically pushing the water, we use selective ion exchange membranes and an electric field to specifically separate ions based on their charge.
Right.
These methods are commonly employed for removing salts from water and for achieving very high levels of deionization.
Interesting. So it's a targeted approach for charged contaminants. What about the third group, driven by concentration differences?
This includes forward osmosis and membrane distillation.
Okay.
In forward osmosis, water naturally moves across the membrane from a solution with a lower concentration of dissolved substances to one with a higher concentration, all thanks to the natural phenomenon of osmotic pressure.
Okay.
Membrane distillation, on the other hand, uses a temperature difference across a hydrophobic membrane.
Okay.
Warm water on one side evaporates,
Okay.
and the vapor then passes through the membrane and condenses on the cooler side. effectively separating the water from non-volatile contaminants.
So FO is harnessing the power of natural concentration gradients, and
Yes,
MD is leveraging heat.
exactly.
And the final group involves chemical potential differences.
Precisely. Prevaporation and membrane contactors operate based on differences in chemical potential. In prevaporation, a specific component from a liquid mixture dissolves into the membrane material, then diffuses through it, and evaporates on the other side, allowing for the separation of volatile substances. Membrane contactors facilitate efficient contact between two immiscible phases, like a liquid and a gas, without actually mixing them, enhancing mass transfer for processes like gas absorption or stripping.
Okay, that gives us a really broad view of the diverse world of membrane filtration.
It does.
Now, to truly grasp how these work in practice,
Yes.
we need to understand some key terms that kept popping up in our materials.
Okay.
Let's start with flux.
Right.
What exactly does that tell us?
Simply put, flux is the rate at which a liquid or gas passes through a specific area of the membrane over a given time. It's essentially a measure of the membrane's productivity.
Okay.
A higher flux generally indicates a more efficient process.
Right.
And logically, if you increase the total surface area of the membrane available for filtration, you'll increase the overall amount of purified water or gas you can obtain.
That makes intuitive sense. More filtering surface, more filtration.
Right.
What about pressure?
Okay.
We've talked about it as a driving force.
Yes.
But are there other important aspects to consider?
Well, as we discussed with the pressure-driven membranes, pressure is the force that overcomes the resistance of the membrane itself.
Mm-hmm.
And in cases like reverse osmosis, the osmotic pressure of the concentrated solution.
Yeah.
It's the push that forces the water from the less pure side to the more pure side. The specific pressure required is a key design parameter for each type of membrane filtration.
Right. Now, a term that appeared very frequently and seems to be a major concern is fouling.
Yes.
It definitely sounds like the nemesis of membrane filtration.
You've hit the nail on the head.
Mhm.
Fouling is arguably the most significant operational challenge in membrane filtration.
Yeah.
The accumulation of unwanted materials, contaminants,
Right.
on or within the membrane surface.
Right.
This buildup obstructs the flow of water, leading to a decline in flux over time
Okay.
and requiring more energy to maintain the desired output.
Right.
The type of fouling you predominantly encounter can actually act as a diagnostic tool, indicating the primary contaminants present in your source water
Right.
and potentially guiding pretreatment strategies.
That's an interesting way to think about it, fouling as a diagnostic. Now, related to fouling, we saw the term concentration polarization. What's that all about?
Concentration polarization often precedes or significantly contributes to fouling.
Okay.
As water permeates through the membrane, dissolved substances that are rejected by the membrane begin to accumulate near the membrane surface. This creates a thin layer where the concentration of these retained substances is much higher than in the bulk solution.
Okay.
This concentrated layer can hinder the passage of more water
Okay.
and can also significantly increase the risk of scaling and other forms of fouling.
Right.
It's like a traffic jam of contaminants right at the membrane interface.
Okay, so it's a buildup of rejected materials creating a bottleneck. Another term mentioned was Donan potential, especially with nanofiltration and reverse osmosis. That sounded a bit more complex.
The Donan potential is indeed a bit more nuanced.
Mm-hmm.
Imagine the nanofiltration, or RO membrane, has tiny electrically charged components embedded in its active layer.
Okay.
When ions in the water get close to these charged sites, they're either attracted or repelled,
Right.
leading to a localized buildup of charge near the membrane surface.
Okay.
This electrical imbalance across the membrane is the Donan potential. Up to a certain point, this can be beneficial, as it can enhance the membrane's ability to selectively reject certain ions.
Right.
However, if this potential becomes too strong, it can worsen concentration polarization
Right.
and increase the likelihood of scaling and fouling.
Interesting how these electrochemical effects come into play.
Mm.
Finally, the Langeler Saturation Index, or LSI.
Yes.
What's its role in all of this?
The LSI is a really practical tool for predicting the scaling potential of water, specifically the risk of calcium carbonate precipitation. It essentially tells us whether the water is likely to deposit calcium carbonate, forming scale on the membrane surface, or if it might even be corrosive to the system. Regularly monitoring and, if necessary, adjusting the LSI of the feed water is crucial for preventing scaling and ensuring the long-term performance and integrity of the membrane system.
So, understanding the LSI allows us to proactively manage one of the major causes of fouling. That leads us directly to the significant challenge of fouling itself. Our sources really emphasize this as the primary hurdle in membrane filtration.
Absolutely. Fouling is the Achilles heel that impacts efficiency, drives up operational costs due to increased energy consumption and cleaning requirements,
Right.
and ultimately shortens the lifespan of the expensive membranes.
Right.
It's a multifaceted problem with various manifestations.
The sources categorize membrane obstruction into three types: reversible, irreversible, and irrecoverable. Can you break those down for us?
Certainly. Reversible obstruction is the most benign, relatively speaking. It's typically caused by particles simply accumulating on the membrane surface. The good news here is that this type of fouling can often be effectively removed through physical cleaning methods, such as backwashing, where we reverse the flow of water to dislodge the accumulated particles. After a successful backwash, the membrane's original flux can largely be restored.
Okay, so a relatively straightforward fix.
Right.
What about irreversible blockage? That sounds more problematic.
Irreversible blockage occurs when particles actually enter and become trapped within the pores of the membrane structure.
Oh, okay.
Simple physical washing isn't sufficient to remove them. Chemical cleaning, using specific solutions designed to break down the phthalates,
Okay.
is usually required to attempt to dislodge these lodged particles. However, even after chemical treatment, the membrane might not fully recover its initial performance.
And then there's the dreaded irrecoverable fouling.
Yes.
That sounds like the end of the line for the membrane.
Unfortunately, yes. Irrecoverable fouling signifies a state where neither physical nor chemical cleaning methods can effectively restore the membrane's performance to an acceptable level.
Right.
The membrane becomes so severely compromised that it has to be permanently taken out of service and replaced. This really underscores the economic and environmental importance of preventing fouling in the first place.
Absolutely. Prevention is key.
Yes.
Now, our materials also detailed 5 distinct types of fouling based on their root causes.
Yes.
Let's delve into those. First is particulate and colloidal fouling.
As the name implies, this type of fouling is caused by substances larger than the membrane's pore size,
Okay.
such as suspended solids and colloidal particles present in the water. These accumulate on the membrane surface, forming a filter cake layer,
Okay.
or they can become lodged at the entrances of the pores, physically blocking the flow of water. As we mentioned earlier, this type of fouling is often reversible and can be quite effectively managed through regular backwashing.
That's good to know. The next type is adsorptive fouling. What's happening at a molecular level there?
Adsorptive fouling involves the adhesion of smaller molecules,
Okay.
such as dissolved organic matter, including natural organic matter, synthetic organic compounds like drug residues, or surfactants like detergents, onto the surfaces within the membrane pores.
Wow.
Because these molecules are essentially chemically or physically sticking to the membrane material,
Okay.
simple physical washing is often ineffective. Chemical cleaning, using specific reagents designed to break these bonds and detach the adsorbed substances, is usually necessary. What's important to note is that this type of fouling can accumulate over time and can even become permanent if the membrane's adsorption sites become saturated or if the adsorbed material undergoes chemical transformations.
So it's like these tiny molecules are stubbornly clinging to the membrane material. The third type is biological fouling or biofouling. This seems like a particularly complex challenge.
It is indeed. Biofouling occurs when microorganisms, such as bacteria and fungi, settle on the membrane surface and begin to multiply, forming a complex three-dimensional structure known as a biofilm. These biofilms are not just composed of the microorganisms themselves, but also their extracellular polymeric substances, or EPS,
Right.
a slimy matrix made up of polysaccharides, proteins, and DNA, which provides structural integrity and protection to the microbial community.
Okay.
Biofouling is often very difficult to eradicate completely and may require a combination of both physical and chemical methods, often involving harsh chemicals. Long-term control strategies include careful nutrient management in the feed water to limit microbial growth, implementation of regular and effective cleaning protocols, and pretreatment steps like disinfection to reduce the initial microbial load. There's also ongoing research into bioresistant membrane materials.
That EPS matrix sounds particularly resilient.
Kiwi.
Next up is scaling.
Yes?
We touched on this earlier with the LSI.
Yes. Scaling is the precipitation and crystallization of inorganic salts on the membrane surface when their concentration in the feed water exceeds their solubility limit. Common scale-forming ions include calcium, magnesium, barium, iron, and manganese.
Right.
particularly problematic in hard water sources. These mineral deposits can effectively clog the membrane pores and significantly reduce the permeate flux. Chemical cleaning with acidic solutions, such as citric acid or hydrochloric acid, is typically employed to dissolve these inorganic scales. The frequency of scaling depends heavily on the water chemistry and the operating conditions.
And finally, we have gel formation. What conditions lead to that?
Gel formation typically occurs when the feed water contains a high concentration of larger macromolecules, such as proteins and polysaccharides. Under certain operating conditions, particularly at higher concentrations near the membrane surface due to concentration polarization,
Okay.
these macromolecules can form a viscous, gel-like layer on the membrane surface. This is more commonly observed in ultrafiltration and nanofiltration systems.
Right.
This gel layer acts as an additional barrier to water flow, causing a substantial decline in the permeate flux. Physical cleaning methods are often insufficient to remove this dense layer,
Right.
and more aggressive enzymatic or alkaline chemical washing might be required to break down its structure.
So, a wide array of fouling mechanisms, each presenting its own set of challenges. It's clear that maintaining optimal membrane performance requires a proactive and multifaceted approach. What are the primary strategies for cleaning fouled membranes and, even better, preventing fouling from occurring in the first place?
The two main pillars of maintaining membrane performance are periodic chemical cleaning
Right.
and the implementation of preventative chemical methods.
Okay.
Periodic chemical cleaning, often abbreviated as CIP or cleaning in place, involves circulating specially formulated chemical solutions through the membrane system at regular intervals to remove accumulated volant and restore membrane permeability.
And as we discussed with the different types of fouling, the cleaning solutions need to be tailored to the specific foulants, right?
Precisely. Acidic cleaning solutions are primarily used to dissolve inorganic scales,
Okay.
such as calcium carbonate and metal oxide precipitates, which are common in hard water or water with elevated levels of iron and manganese at higher pH.
Right.
Alkaline cleaning solutions are effective at removing organic pollutants,
Right.
including natural organic matter, oils, and the organic components of biofilms. These often contain chemicals like sodium hydroxide, sodium carbonate,
Okay.
and sometimes biocides to disinfect the system.
Okay.
Lastly, oxidizing cleaning agents, such as sodium hypochlorite or hydrogen peroxide, are used to prevent biological growth and to break down organic matter and microbial biofilms.
So a targeted cleaning regimen is essential.
Yes.
Now, what about preventing these problems from arising in the first place through chemical means?
Absolutely. Prevention is always the most cost-effective and sustainable strategy. One common preventative measure is the use of anti-scalants, which is chemicals added to the feed water in small concentrations to inhibit the precipitation and crystal growth of scale-forming salts like calcium carbonate, calcium sulfate, barium sulfate, and silica. Biocides, both oxidizing like chlorine-based compounds and non-oxidizing, are frequently used to control the growth of bacteria and prevent the formation of biofilms on the membrane surfaces. Additionally, in RO systems, it's standard practice to dose sodium pabisulfite into the feed water before the RO membranes. This chemical effectively reacts with and neutralizes any residual chlorine from upstream disinfection processes, as chlorine can be very damaging to the thin film composite membranes used in RO.
So it's a combination of pre-treating the water
Yes.
and having cleaning protocols in place. Now, once these sophisticated membranes are manufactured, they can't just be used as individual sheets or fibers, can they? They need to be incorporated into practical units.
Right.
That's where membrane modules come into play.
Exactly. A membrane module is essentially a packaged unit that houses the membrane material in a specific configuration, along with the necessary infrastructure for the feed water to enter,
Right.
to permeate the purified water to exit, and the concentrate, the rejected materials, to be removed.
Yeah.
The design of the module is critical for maximizing the membrane surface area within a given volume, promoting efficient flow distribution, minimizing fouling tendencies, and facilitating cleaning and maintenance.
Our sources highlighted 4 primary module designs. Let's begin with flat sheet modules.
Okay.
What are their characteristics and typical applications?
Flat sheet modules feature membranes arranged as flat sheets, often with spacers in between to create flow channels. The flow of water can be either cross-flow, where the water flows parallel to the membrane surface, or dead-end flow, where the water is forced directly through the membrane.
Okay.
Flat sheet modules generally offer a lower membrane surface area per unit volume compared to other designs.
Right.
However, they are relatively simple to manufacture and clean, making them well suited for laboratory-scale experiments, pilot plants, and certain niche applications.
Makes sense for smaller scale testing and specialized uses.
Right.
What about spiral wound modules? We hear about these quite a bit.
Spiral wound modules are indeed very widely used, particularly for large-scale RO and NF applications.
Okay.
They're constructed by layering flat sheet membranes and spacer materials and then wrapping this assembly around a perforated central pipe. This spiral configuration allows for a very high membrane surface area to be packed into a relatively compact volume. Spiral wound modules are known for their good resistance to fouling compared to some other designs,
Right.
high efficiency in removing dissolved substances,
Right.
and relatively straightforward installation, replacement, and cleaning procedures. It's quite remarkable that the world's largest seawater reverse osmosis desalination plant, the Wastewater plant in Israel,
Oh, wow.
which produces an astounding 640,000 cubic meters of potable water per day,
Wow.
relies heavily on spiral wound membrane technology.
That scale really underscores their effectiveness. The next type is tubular modules.
Okay.
What are their distinguishing features?
Tubular modules consist of membranes formed into tubes with a diameter typically greater than 2 millimeters. They share similar cylindrical geometry with capillary and hollow fiber membranes, but have larger individual channels.
Okay.
Tubular modules are particularly advantageous for treating feedwaters with high concentrations of suspended solids and other particulate matter,
Right.
because their larger flow paths are less susceptible to clogging. While they tend to experience less particulate fouling,
Right.
they often offer a lower membrane surface area per unit volume compared to spiral wound or hollow fiber modules and can be more challenging to manufacture.
So the wider channels are a key feature for handling more challenging water sources.
Yes.
And finally, we have hollow fiber modules.
Hollow fiber modules utilize membranes in the form of very thin hollow fibers, with diameters typically less than 2 millimeters. These fibers can be arranged in bundles, and the water can flow either from the outside of the fibers into the lumen, inside out,
Okay.
or from the lumen outwards, outside in.
Okay.
Hollow fiber modules offer an exceptionally high membrane surface area per unit volume, making them very efficient for a wide range of applications,
Right.
including MF, UF, and some RO systems.
Right.
While the manufacturing of hollow fiber membranes and their integration into modules can be more technically demanding, they are currently the most prevalent type of commercial membrane module used in diverse water and wastewater treatment processes globally.
It's fascinating to see how the design of these modules is so intricately linked to their performance and suitability
Yeah.
for different applications and water qualities. The engineering involved is really impressive.
Absolutely. The selection of the appropriate membrane type and module configuration is a critical decision in designing an effective and efficient water or wastewater treatment system.
Right.
And it's often a result of careful consideration of the specific treatment goals and the characteristics of the water being treated.
Right. Well, this has truly been a deep dive into the world of membrane filtration.
It is.
We've explored the fundamental principles, the various types of membranes and their driving forces,
Right.
the critical terminology,
Yes.
the persistent challenges of fouling and the strategies to combat it,
Yes.
and the different ways these membranes are packaged into practical modules.
And as our sources clearly indicated, the application of membrane processes in water and wastewater treatment has seen remarkable growth over the past 2 decades.
Right.
And with increasing demands for clean water globally, this trend is undoubtedly set to continue.
Considering the sheer diversity of membrane filtration technologies and
Right.
the ongoing complexities of managing fouling, it really prompts the question, what groundbreaking innovations do you anticipate having the most significant impact on ensuring sustainable water resources in the future?
That's a great question.
Will it be the development of entirely new membrane materials with enhanced properties?
Right.
The design of more efficient and fouling-resistant module configurations?
Right.
Or perhaps the implementation of smarter, more predictive fouling prevention and cleaning strategies?
Yeah.
It's certainly a critical area for ongoing research and development.
Indeed. It's a very dynamic field where continuous innovation is pushing the boundaries of what's achievable in water purification and resource recovery.
Thank you for joining us on this in-depth exploration of membrane filtration.
It was a pleasure.
We truly hope you found this deep dive informative and insightful. If you did, please don't forget to subscribe to the Environmental Science and Engineering podcast channel so you don't miss our future discussions.
Yes, please do.
And feel free to leave us a comment with your thoughts or any questions you might have. We always value your feedback.
We do.
We look forward to delving into another fascinating topic with you next time. Until then, goodbye.
Goodbye, everyone.
Goodbye, everyone.